Hi, in this video we'll be focusing on the physics of strings. This long question is actually very well laid out, so it makes sense that the first part, A, asks us to state Hooke's law, which we're going to need throughout the question, and to give some description of the potential energy of a stretched string. So let me remind you of Hooke's law. The force exerted by the string is the extension from its natural length times some constant. For the energy of a string, they don't want just to state the formula itself, that's half k y squared, which is a formula definitely worth knowing by heart. But don't forget that you can always get it by integrating Hooke's law. So it would be a good idea to somehow describe the energy of the string, to say something along the lines that as the rope is stretched, that the energy is stored in the elastic material by doing work against the atomic bonds between the atoms, and this energy can be later released. These two equations are very important, so I'm going to pin them to the corner. Section B is basically a numeric warm-up. In this part, Alice is hanging from the rope at a distance 26 meters from the bridge or wherever this top level is, and the rope's natural length is 10 meters, so it's extended by 16 meters. We can see down here that, while she weighs 50 kilos, there's gravity in her acting downwards, and there's the force from the string acting upwards. And as poor Alice is hanging down here, at least she's at rest, which is great news for us, because that means that forces are balanced. So we can write the equation that mg equals the force from the string, so that's k times the extension, 26 minus 10. If I plug in the numbers, what I get is 31.25 newtons per meter. And finding the potential energy is now just a matter of plugging in to this equation here, which I've rewritten using our coordinate x from the top here rather than the y, which is just the difference between the natural length and the actual length. Again, putting in the numbers, we get 4,000 joules. From section C onwards, Alice decides to go bungee jumping. In section C itself, we are supposed to describe her acceleration from the point when she jumps off the bridge until she reaches the bottom of the motion. So let me draw the force diagrams at 6 different times. The weight is the same at all 6 points. However, the force from the spring, here, F, changes. So before the string is even taut, that's here, it's just a free fall and no force upwards from the string. But from this point, below that point, the force actually increases as we get further from this position, until it reaches its maximum. That's this bottom point here. That means that the resulting forces are as follows. So the net force at the beginning is downwards, but then it decreases in magnitude. It's more upwards and upwards as this force of the string becomes stronger and stronger. Now would be a great time to stop the video and, bearing in mind these diagrams we've drawn, to try and find the acceleration in these 3 regions here. Acceleration, that means direction and magnitude. At the beginning, before the string even starts acting, obviously that's free fall, so acceleration downwards and constant, g in particular. In the second region, when the string already becomes taut, so it starts acting, but the forces haven't balanced it, so gravity is still stronger than the force of restoration, so the acceleration will be still downwards, and we can see that from the net force. So remember that net force and acceleration are basically the same thing, just but for a constant, the mass. And in the last third region here, again, we can see that it's going to be upwards because the force is upwards, but now it's increasing. So you can actually see that from this tendency here, that the force from here to there is growing, so we'll get increasing acceleration. Before we plunge into the rest of the question, let's think about energy conservation. Whenever they ask about maximum speeds, where they occur in maximum positions, solutions which use conservation of energy are going to be more elegant than ones using maybe the Suvat equation or the equations of forces. Before she jumps off, her gravitational potential energy is mgx, so note that I set the potential energy to be 0 at the bottom. Kinetic energy 0, she's not moving, and this string is not acting at all, so the potential energy of the string is 0 too. However, in the bottom, at an arbitrary distance x from the top, The gravitational potential energy is 0. We set it to be 0, so it must be 0. The kinetic energy corresponds to whatever speed it has at the point. And the potential energy of the spring we just plugged into this useful formula with y, the distance from the natural length, being x minus 10. 10 is our natural length. And since energy is conserved, we can equate these two energies. So we have that mgx equals half mv squared plus spring energy at the bottom. And now this is a key equation we're going to be using, because it links Alice's position and speed at every given point. Having found this equation of motion, we are now all set to answer the rest of the questions. So in section D, they ask what the speed is at position x equal 15 meters. Remember, we have an equation which has x and v as the only two variables in it, so let's just plug in. Here we go, so that's 15 for x, 5, that's 15 minus 10 from here. The next step, all the other numbers, and finally we should get that v equals about 17 meters per second. Now similarly in part E, they ask at what position is the body at rest, basically where does it turn around, where's the bottom of the trajectory. At rest means kinetic energy is 0, this term here is going to be 0, so all we're left with is mgx and half k x minus 10, the whole thing squared, that's down here. And that's a quadratic equation in x, and as you see, that has two solutions, 2 meters and 50 meters. So usually in these kinds of problems, when we get two solutions from a quadratic equation, we have to pick one, and good practice is always to try and write down why we have chosen the one we have chosen. Here we clearly see that the first solution is in a region where the string is not even acting, so it can't be it, and it must be 50 meters. In section F, the question is what the maximum speed reached during her jump was, and where, at what age it was reached. Now, the difficult part about this is somehow like writing it down, putting it on paper. So you can now pause the video and try to write that fact that speed is maximum as an equation. One way to do this would be to write that the acceleration is 0, because if the function v is maximum, then we know that's going to occur when its derivative is 0. The dv by dt, the derivative of a speed with respect to time, well, another word for that is acceleration, so we can write a equals 0. If acceleration is 0, that means that the forces are balanced. Force of gravity equals the force exerted by the rope. And once again, when we plug in the numbers, we get 26 meters. So now we know where this maximum speed occurs, but we don't know the speed itself yet. But luckily enough, we have our new best friend, the red equation. And when you plug in, we get that the speed at position x equals 26 meters. I've just plugged in 26 for here 26, and 16 for 26 minus 10, that's here, 16. Plug in all the other numbers in this line, and finally I get that v equals 19 meters per second. So on to G, where we are supposed to find the maximum acceleration and where it occurs. If you think about it, we've basically answered this question already. If you remember our diagrams, we said that the force and therefore the acceleration was increasing before we reached the bottom point where the force was maximum while the weight stays the same everywhere. The net force was the biggest here, and hence this must be the point of maximum acceleration. So that's at the bottom, this acceleration points upwards, and it's when speed is 0 and position is 50. We've found that before in one of the previous sections. Now by Newton's second law, at this point, we have that ma has to equal the difference between these two forces. Now this F, which here is F max, that's the force of the string, that's k x minus 10. Now downwards is force of gravity. So when you subtract the two, by Newton's second law, we get mass times acceleration. Now plugging in the numbers for g, m, and x, we get that a equals 15 meters per second. And finally, in part H, graphing acceleration versus position. We don't really need to do much work here either, because if you look at the net force diagrams, and again, remember that net force is very similar quantity to acceleration, except for constant mass. So we see that it's constant here before the string is stored, and then it goes up like this in a straight line. So if we take downwards as negative, this is the graph we should get. Downwards 10 meters per second, or 9.81, and then gradually downwards. Note that we have all these points from previous sections. 50 meters for the bottom, we know that 10 meters is the natural length of the string, then negative 15 meters per second is the maximum acceleration from the previous section. So we just took all the information we had and we put it together into this nice graph. To summarize, in this video we reviewed some of the key concepts of strings, notably Hooke's law and potential energy on a string. And we also learned an important lesson about how energy approaches and kinematic approaches can work together. But as a rule of thumb, wherever we see accelerations, it is a good idea to draw force diagrams and maybe use Newton's second law. With speeds and positions, it might be better to equate the energies, as that usually leads to neater solutions. Being able to decide which of these two approaches is better is just a matter of practice and physical intuition.